Okay, in the previous lecture, we looked at ordinary generating functions. And then, one example. Now, we will look at a couple of more examples before going into further topics. So let us start with another example. So here is our example 2. So again, we have our 5 devotees of the blue goddess. Okay. So now what they do is that they change their strategy of conversion. So they started converting in a different way. So what they do is that on the first day, they will preach to one recruit who joins. Okay. So the first morning, right after the religion was formed, the first morning they will convert only one person. Now the new converts follow the same strategy, right? Once they join the religion, the next morning they will preach to one person, then recruit. Then every devotee from his second morning onwards recruits 9 others. So they have increased the pace. So the first day it will be relaxed, but then next day onwards they are more energetic and they are going to convert 9 people every day morning. Now once converted, all the converted people remain the devotees. Nobody changes their opinion. Now in this case, how many devotees will be there after the nth day? Okay. So a slight modification from the previous question, right? So we started with our 5 devotees of blue goddess who wears blue t-shirts, right? And then they convert people in the following way, right? So first day they will preach to only one person. Second day onwards they will introduce 9 more persons, and whoever has converted, there next morning, right, the first day, they will convert one person, and then the next morning onwards they will convert 9 others. So similar to the previous question, we can form a recurrence relation and then try to solve it, right? So using the generative functions. So let us see how we can form the recurrence relation. I recommend that you really try to do it on your own. Then once you give it a try, come back here and continue. So we have the following observation that if dn we denote the devotees after n days, then d0 is 5, right? The 0th day, right? When the religion is formed, there are 5 devotees. And at the end of the first day, right, d1, you have 10 devotees because they converted, each of them converted one more person. So I have 10%. Now nobody is going to give up the religion after they join it. So therefore, at the end of day 1, you have 10. Then what is the recursive formula, right? So we have d0 is 5 and d1 is 10. Now can you find out formula for dn, right, where n is greater than or equal to 2? So if you think about it, you will see that, okay, so the first day they convert 5, but second day onwards each of them converts 9 others, right? So therefore, whoever joins this day, right, on the n-1th day, they convert, whoever is present there, they will all convert one person at least, right? So everybody converts 1. So all the dn-1 people will convert at least one person. So therefore, you have 2 into dn-1 person, right? The end of the day, you have 2 into dn-1. Now, each person who was there in the previous, right, so this is not the first day for people, they will all convert 8 more people, right? Because they in total they convert 9, so 1 is already counted, so they convert 8 more people. So people who are the second day, which is dn minus 2, right? Each of them, right? Dn minus 2 of them are having the second day now. So they will all converge 9 people. So therefore 8 more new people other than themselves. So therefore we have 2 into dn minus 1 plus 8 into dn minus 2 is dn, right? Because whoever is there, then everybody converts one person's, and then each of the persons who is having the second day or more, right? All those people will convert 8 more others. So that, therefore we have 8 into dn minus 2 plus 2 into dn minus 2. So therefore we have the recurrence relation. Now we can use the method of generative function. So how do you do that? For that we multiply by x raised to n on both sides of the recursion relation, and then sum overall n greater than or equal to 2, right? So summation dn x raised to n greater than or equal to 2 is equal to 2 times summation n greater than or equal to 2 dn minus 1 x raised to n plus 8 times dn minus 2 x raised to n greater than or equal to 2. Why n greater than or equal to 2? Because the recursion formula holds for n greater than or equal to 2, and we have the term dn minus 2, right? So the index only starts from 0. So I have n is greater than or equal to 2. Now, so if you look at the the form for summation dn, right, x raised to n, from that, which is, let's say, d of x, if I denote by d of x summation dn x raised to n, right, d of x is equal to summation dn into x raised to n, dn into x raised to n. Then we have d of dn x raised to n greater than or equal to 2 has the first 2 times missing, which is dn minus 1x, I mean d1x and d0. So we subtract that to get the LHS, right? d of x minus 10x minus 5, because d1 is 10 and d0 is 5. On the other hand, on the right side, you have 2 times summation dn minus 1 x raised to n. I take 1x outside. I get 2x into d of x minus 5, because the first term is missing from the summation. And then you have, from the last one, you can take x square outside. You will get a d of x there. So I get 8x square d of x. So therefore, I get the formula. Now simplify this for d of x. I get d of x is equal to 5 divided by 1 minus 2x minus 8x square. Now the the polynomial 1 minus 2x minus 8x square can be easily factored. So I will get as 1 plus 2x into 1 minus 4x. Right? So this will be written as a method of partial fractions. We can write it as alpha by 1 plus 2x plus beta by 1 minus 4x. So we solve for alpha and beta. We will get alpha is equal to 5 by 3 and beta is equal to 10 by 3. Okay, this is something you can do from what we have done before, right? So you take the cross product, compare the coefficients, and then we will get these equations. After solving which, you will get alpha and beta. Now, therefore, d of x is equal to 5 by 3 into 1 by 1 plus 2x plus 10 by 3 into 1 by 1 minus 4x. Now this is now easy, because coefficient of x raised to n in d of x I can find out by expanding these two functions to series. So I will get this as 5 by 3 into minus 1 whole raised to n 2 raised to n, because that is the 1 by 1 plus 2x goes to minus 2 x whole raised to n, right? So it is minus 1 whole raised to n 2 raised to n. And then you get 10 by 3 into 4 raised to n, because 1 by 1 minus 4x goes to 4 raised to n x raised to n, summation 4 raised to n x raised to n. So the coefficient of x raised to n in d of x is precisely this, right? So 10 by 3 into 4 raised to n minus plus minus 1 whole raised to n, 5 by 3 into 2 raised to n. So d0 is 5. We can verify by putting n is equal to 0. For example, I will get 5 by 3 plus 10 by 3, which is 15 by 3, which is 5. And d1 is again n is equal to 1. I will get minus 10 by 3 plus 40 by 3, which is 10. This is also correct. So similarly, we can verify for other values. So I get a closed formula for dn. Right? So now we see how powerful this method is. Right? We look at another famous sequence, which we call the Hemochandra sequence. Right? So Hemochandra sequence, if you remember, is also called the Fibonacci Hemochandra or Hemochandra Fibonacci sequence. And this sequence satisfies the recurrence relation, as we already know, is Hn is equal to Hn minus 1 plus Hn minus 2, right? So, starting conditions, initial condition can be H0 is equal to 1, H1 is equal to 1, and then you can continue. I mean, you have a slightly different way of defining the initial conditions, because sometimes people start by 1, then 2, and then etc. Right, 1 1 2 etc. Sometimes it will start with 0 1 etc. Right. So this will make only very minor difference, because just shifting in the index. So we don't have to worry about that. We will assume that this is our current initial condition. So Hn is equal to Hn minus 1 plus Hn minus 2 for n greater than or equal to 2. H0 is 1, H1 is 1. So we can do, now let us compute this h of x in a slightly different manner, right? We know that h of x is summation hn x raised to n, right? Now let us look at the coefficient of x raised to n in h of x minus x times h of x minus x square times h of x. Now why do I look at this? Because hn equal to hn minus 1 plus hn minus 2, that identity is there. Now if I look at coefficient of x raised to n in h of x, that is basically hn. Then coefficient of x raised to n in x times h of x, x is basically hn minus 1. And coefficient of x square times coefficient of x raised to n in x square times h of x is basically hn minus 2, right? So this is clear, because x square basically shifts the times by 2, so therefore I get a coefficient of x raised to n will be hn minus 2. Now hn minus 1 minus hn minus 2 is 0, because for n greater than or equal to 2, we have this identity, right, satisfied by the Hemochandra series or Hemochandra sequence. Hn is equal to hn minus 1 plus hn minus 2. So therefore we have this coefficient of x raised to n for this part is 0, right, for n greater than or equal to 2. Now, what for n is equal to 0, what is the coefficient of x raised to 0? Right, coefficient of x raised to 0 in this is precisely h0, right, because when it's equal to 0, we have only the term from h0 will not get cancelled, right? So therefore that is h0, but that is 0. So therefore the reason we assumed h0 to be 0 is to make this slightly simpler. Now coefficient of x raised to 1 in the same is that you can take h of x. So h1 will survive, right, h1 x, and then h0 x from the second time will also survive, right? But because h0 is 0 and h1 is 1, h1 minus h0 is basically 1. That is the coefficient of x raised to 1, right? Because coefficient of x raised to 1 in the second term is basically h1, right? Because there is a shift. The second term is h0 because there is a shift. The first term is h1, and third term there is no h0 or h1, right? I mean there is no x, right? Because we are multiplying by x square. So, so x0, coefficient of x raised to 0, coefficient of x raised to 1, and coefficient of x raised to n we have got. So therefore, we have the complete information about the difference of this power series, right? So h of x minus x times h of x minus x square times h of x is actually equal to, so the equation, right, in x, which is with coefficient 0 for whenever the power of x is at least 2, coefficient 0 whenever the power is 0, and coefficient 1 when the power is 1. So that is the polynomial x. So therefore, we get this difference of the formal power series, these three, is precisely x, right? So now I get a formula for h of x immediately by putting h of x together. So x divided by 1 minus x square. Right? So h of x is equal to x by 1 minus x square. If I write it as x by 1 minus alpha x into 1 minus beta x, by the method of partial fractions, we can solve it, and then we will get, before applying the method of partial fractions, we can first solve for the 1 minus x minus x square decomposes into 1 minus alpha x and 1 minus beta x by alpha equal to 1 plus root 5 by 2 and 1 minus root 5 by 2. This is the solution of quadratic equation. So therefore, we can immediately get it. And the roots alpha and beta. And once you have this, we use the method of partial fraction, right? So once you write down, we can show that this actually reduces to the following. Okay, I can write it as, so this computations now is routine, so therefore I leave it to you. I don't want to spend time on working out this minor details. So you work with this, and if you have any questions, get back to me, right? So therefore, x by 1 minus alpha x and 1 minus beta x, I can write as 1 by alpha minus beta into 1 minus alpha x minus 1 minus 1 by 1 minus beta x. Okay, so if you solve it like this, then this 1 by alpha minus beta is precisely root 5. 1 minus, is precisely root 5, and then I will get this 1 by 1 minus alpha x minus 1 by 1 minus beta x, where alpha and beta are exactly like we have said before, right? 1 plus root 5 by 2 and 1 minus root 5 by 2. Then solving for, not solving. So now we need to just find out the coefficient of x raised to n in this, right? That is easy because I have it is in a nice form, 1 by 1 minus the alpha x and 1 by 1 minus beta x. So which is, coefficient is x alpha raised to n, and the second one is beta raised to n. So therefore, I have 1 by root 5 into alpha raised to n minus beta raised to n is the coefficient of x raised to n. So hn is now 1 by root 5 into 1 plus root 5 by 2 whole raised to n minus 1 minus root 5 by 2 whole raised to n. Right? So there is a bracket which I have missed. Yes, so that is it. So we have now closed formula for computing hn. And now it may be interesting to see that this is always an integer, right? So 1 plus root 5 by 2 whole raised to n minus 1 minus root 5 by 2 whole raised to n divided by root 5 is always an integer, because hn is our Fibonacci or Hemochandra sequence. Okay, so I will give you a couple of homework questions. So use generative functions to solve the following. So we have the following situation. So there is a nice pond or a lake. Let's say it's a magic lake. So this magic lake has this property. If you throw, let's say, 50 lotus flowers to the lake, then every day the number of flowers grows by 4 times at the midnight. So every night, the number of flowers multiplies by 4. Okay, so if there is 50, then next morning you will see 200 of them. So in the morning, 100 flowers will be picked for sale. Okay, so people use this, that you put 50 or whatever, let's say some flowers. Next day you have 4 times, so you take some of them and then sell it. So if I start with 50, then first day I get, first night I will get 200. Then I pick up 100 and sell it. So then the remaining 100 will be there. That will multiply by 4 times, right? So 4 into 400, then I again take 100. You have remaining 300. And then this way I keep on doing, right? Now after 30 days, how many flowers will be there in the lake, right? And how many how many will be there after n days in general. So try to find the recursion formula, right, and solve it using the method of generative functions. Second question asks you to solve the recursion relation. Bn plus 2 is equal to 3 times Bn plus 1 minus 2 times Bn. Now, the initial conditions are assumed to be B0 is 1 and B1 is equal to 1. Okay. Now, again, use this information, find the generative function for B of x, which is the sequence, which is the generative function for the sequence Bn. And using this, deduce an explicit formula for Bn, right? From the generative function, we want to find a closed formula for Bn. That question asks you to do the following. Given a sequence, let's say Fn, and this Fn satisfies the following recurrence relation, right? So summation I equal to 0 to k, fi into fk minus I is equal to k plus 2 choose 2. Okay? This recurrence is satisfied by fi for k greater than or equal to 1. And f0 is 1. Now find f of x, the generative function for the sequence fn, and then use it to deduce a formula for fn. Okay, and then compute f4 using this identity. So this is what we want. Now we look at the combinatorial meaning of the product of generative functions. So suppose you are given two sequences, right? Let's say an and bn, which represent the number of ways, let's say two different combinatorial structures on sets can be built, okay, on an n-element set. So given an element set, I want to make let's say using this n-element set, I want to make let's say permutation. Right? Similarly, given n as a parameter, I want to say what is the number of triangulations and n-sided polygon can have, right? So these kind of things can be represented by sequences A, N, and B. Now, we define Cn to be the total number of ways. Okay. So given an n-element set, let me take so let us say that you have this set 1 to n, right? There is an ordering we fix, and then so on this set let's say 1 to n, what I am going to do is that I want to first build a structure of this type A, right? Let's say they're talking about permutation. So I want to make permutations on the set, let's say 1 to I for some I. Then I want to make type B structure, which is in our example, this was we were looking at what the triangulations of a polygon, right? So I want to make and count the polygons, right, and the number of such triangulations, right? So I want to make triangulations of a polygon which can be made out of I plus 1 to n, right? Or like I want to put a structure on the set t is equal to I plus 1 to n. So we have two types of structures, let's say type A and type B, right? So type A structures on an element set, I have an of them, and type B structures, there are bn of them. Now, Cn is defined to be the total number of ways to first build a structure of type A on the set 1 to I, and then a type B structure on the set I plus 1 to n for some I. So for each I, this can be done, right? So from I ranging from 0 to n, I can do this. So I can say that okay, I don't build anything. I put the empty set on which if I can do some structure of type A, I do that. Then for the remaining all n elements, I put the structure B. Or I can say that for one element, one I will take here. The remaining 2 to n minus 2 to n, I will put structure B again. Similarly, I can take the all elements 1 to n and put a structure A on that, and then in the empty set I can put structure B, right? So this way I do for every possible I. Now, if A of x and B of x represent the generative functions for an and bn, and C of x represent the generative functions for Cn, then the claim is that C of x is equal to A of x into B of x, right? The product of the generative functions of A and B will give you the generative function for Cn. And the proof is simple. The proof is that Cn is equal to summation I equal to 0 to n ai into bn minus I. The way we have defined. So what is our definition for Cn, right? So we said that Cn is the number of ways to first build a structure of type A on 1 to I, right? So basically that is AI, right? And then I can put structure of type B on I plus 1 to n, which is n minus I elements are there. So on given any n minus element set, or n minus 1 as the parameter, I have exactly bn minus I structures of type B, right? So therefore, for a fixed I have AI structures I can make here, and bn minus y possibilities to do on the type B structure. So therefore, the total number of possible ways is that I can build any of the AI structures here, any of the bn minus y structures there. So AI times bn minus I structures I can make, right? This is by the product rule of so that we have learned before, right? Now I can vary, right? Because we said that for each I we have this option, right? So I can fix the I to be either 0, 1 or up to n. Therefore, I can range from 0 to n, right? And then each one, like is separate. So they are basically disjoint sets. So I can do the sum rule, right? So I can say summation I equal to 0 to n ai bn minus I, and that is precisely the number of ways to make the C-type structure. So that is precisely Cn, right, on the n element set. Right. So if we define our C-type structures to be built this way, then Cn is precisely summation ai into bn minus I equal to 1 to 0 to n. But then that is the definition of the product of the generative function, right? So we said that a of x times b of x is summation n greater than or equal to 0, right? Summation n greater than or equal to 0, summation ai times bn minus I ranging from 0 to n, x raised to n, right? This is the generative function of the product. But then, what is this? This is precisely Cn, right? So therefore, I have summation Cn x ratio n, which is the generative function for the sequence Cn, right? C of x. So therefore, I get the proof that C of x is equal to f x times C of x. So this is a way to, basically this is a way to interpret what happens when you take the product of two generative functions. And if the generative functions are representing counting sequences for structures, right? So this is, there could be other ways to interpret this, but this is one way that we want to do, right? This is a standard way to do it. And precisely this, right? So we see this as happening, like, you have 1 to n, you basically divide it at, split it at ith position for any I, put, first type structure on 1 to I, second type structure on I plus 1 to n, and then you, do for each I, this you can do, and therefore that is the number of ways to build the structure. Now we can now use this to solve problems. Okay, so here is an example. So there is a short course on, let's say, combinatorial algorithms, which is offered with a duration of, let's say, n days. Okay, so there is an n day course, like, like 30-day course, or 20-day course, or 50-day course, right? Something like that. There is a short course on combinatorial algorithms offered, and it has duration of n days. Now the instructor decides, okay, the first k days will be basic combinatorics. Okay. The remaining days, right, will be algorithms. So the n days are split into two, right? First k days will be basic combinatorics, because we need to learn combinatorics to be able to use in the combinatorial algorithm. So first k days will be combinatorics, remaining will be algorithms. Now 1 day in the first k will be non-instructional day. Okay. So out of the k days, 1 day I will say I will not teach on 1 day. That is 1 day is holiday. That is decided. Then 2 days in the second part, right, will be also for reserved for labs, because without doing labs, we don't want to finish the code. So therefore, we will say 2 days will be labs. Now the question is that how many days, how many ways one can plan this codes, right? So because k can vary, right, and the choice of the holiday can also vary. So therefore, we need to figure out this, right? So first, we note that, right, since we need to have at least 1 day as holiday, right, k must be at least 1, because if there is no day, right, I mean, k cannot be 0, because if there is no day, I cannot choose 1 day as a holiday, right, for the first part. So therefore, k must be at least 1, but it cannot be more than n minus 2, because if there is n day semester, 2 days must be reserved for the holidays in the second part, right? So because we need at least 2 days there, it cannot be less than 2 days. But apart from that, there is no restriction, so I can have k between 1 and n minus 2. Now, let us define Cn to be the number of ways the course can be planned. So what is Cn? Cn is precisely the the number of ways to first so split the n days into two parts, like 1 to k and k plus 1 to n, right? Then choose one holiday for the first part, then 2 holidays for the second part, right? And once you do that, your course is already planned, right? So therefore, for not holidays, 2 days for the labs. So therefore, we have clearly Cn as splitting into k and n minus k, right? And then from the k, I need to choose 1 day. So there is k choose 1 possibilities are there, right? So the choice of 1 holiday for the first part of the course will be k choose 1, which is equal to k. And then the remaining n minus k days are there for the second part, and 2 days I need to do fix it for lab, right? So 2 days I can choose in n minus k, choose 2 possible ways, right? So this is the number of ways to choose 2 days out of the n minus k days. So therefore k into n minus k choose 2. This is the number of ways to design the course. You know, if you have exactly k days for the first part and n minus k for the second part. Now k can vary from 1 to n minus 2 we said, right? So therefore I can sum over all these possibilities. So k equal to 1 to n minus 2, k into n minus k choose 2.